Before I begin, I'd like to thank the organizers of the conference for this opportunity to speak. So I'll be speaking about series invariants for three manifolds and categorification. As a motivation, to an oriented link in 3-sphere, one can associate its Jones polynomial, taking values in Lorentz polynomial ring with integer coefficients determined by its gain relation and the non-normalization. Its gain relation consists of three links differ only locally by the three pictures shown in the equation, and each picture corresponds to a Jones polynomial of that link. And Jones polynomial admits a categorification called Kaufman homology, and this homology is a vector space or abelian group. I is homological grading, and J is quantum grading. The Euler characteristic of this homology is Jones polynomial up to some factor. And this motivates about our categorification of three-manifold invariant. And as for a second motivation is interaction between physics and topology. So in middle of 1950s, four-dimensional Yang-Mills theory was constructed and many years later, Simon Donaldson showed that family of polynomial invariants for smooth four manifold can be defined using the Yang-Mills theory, which was constructed for very different purposes. And in middle of 1990s, Seiberg and Witten constructed a different gauge theory in 4 dimensions. And a few years later, Tobbs, Krohmeimer, and Rofka and others showed that this Seiberg-Witten theory can produce invariants for smooth four manifold, often called Seiberg-Witten invariants. In 3 dimensions, Edward Witten showed using Chern-Simon theory that Jones polynomial, or more precisely Color-Jones polynomial, can be formulated using gauge theory. And this work motivated Reshtikin and Tarayev for rigorous construction of, in particular, this 3-manifold invariant that was predicted by Chern-Simon theory. So I'll be more specific about this 3-manifold invariant. So reiterating what I just said. So inspired by the 3D SL2C Chern-Simon theory formulation of Color-Jones polynomial and the introduction of a quantum invariance of 3-manifold, Reshtikin and Tarayev constructed this 3-manifold invariant using a dance surgery presentation of closed-oriented 3-manifold and Color-Jones polynomial of the surgery link and the quantum group UKSL2C at root of unity in a rigorous manner. And this invariant is often called the WRT invariant, and it's defined at root of unity and takes values in complex field. So to get an idea how this WRT invariant looks like, let's look at a simple example, length space L51. And so there are some fractional powers of Q appearing in several places. And there's also irrational number, square root of 5. And more serious problem is there's this root of unity factor K that appears in the numerator as opposed to in the denominator where it was originally inputted. So due to this lack of integrality of the WRT invariant, it seems hard to categorify. Nevertheless, some years ago, a group of physicists, Gukov, Puchra, Baffa, and later together with Chae, conjecture the existence of a Q-series invariance called G hat of a closed-oriented three-manifold Y having integrality property and giving rise to the WRT invariant. So for Y with vanishing first Betti number, and for every spin C structure of Y, call it B, there's this power series in Q with the integer coefficient, and overall Q factor whose power is rational number and depends on the choice of spin C structure. And the Q lives in the interior of the complex unit disk. So, and the radial limit as Q go to a primitive root of unity of G hat exists, and in this limit, it is conjectured that the WRT invariant of rational homologous three-sphere decomposes as follows. On the right-hand side, there is a sum of the sum end, which contains this G hat, and its coefficient is some complex number, and A and B are roughly spin C structure of Y, and this coefficient depends on the leaking form of Y and order of first homologous group and kth root of unity. So schematically, there is this, so that this is a Q complex plane, and from the origin, as one takes radial limit to a root of unity, one finds the value of the WRT invariant. So one remark is that actually this definition of Z is lacking, but it's still possible to analyze its properties and compute property. Analyze its properties and compute examples. And another result of their work is prediction for categorification. So Z is supposed to admit a categorification. And this is the Y-graded vector space denoted HBPS of Y, and its order characteristic is Z hat. And this HBPS homology group is three-manifold analog of the Kovenov homology, but not much is known about it. And there has been some partial progress on categorification of WRT invariant in a rigorous way by these people. So let's move on to a Plum manifold. So in Plum construction of compact three-manifold, they are characterized by a weighted graph. Each vertex corresponds to a circle bundle over a compact surface of genus G, and is labeled by its genus and the Euler number. An edge is a gluing between two circle bundles in fiber-based exchanging way. And we choose all the base surface to be two-sphere. So, for example, length space LPQ has a linear plumbing graph. And this Euler number AI's come from continued fraction expansion of P over Q. And Prescott sphere 237 has this plumbing graph with this Euler number, or -1, -2, -3, and -7. And alternative perspective of Plum 3 manifold is surgery presentation. So in this presentation, a vertex is replaced by an N-framed on knot, and edge by Hopf link. So for this case, so we just replace each vertex by a knot and link them using Hopf link. And similarly for this Prescott sphere. And moreover, a linking matrix of this surgery link corresponds to a adjacency matrix of plumbing graph. So for negative definite graph, so these are graphs whose signature of adjacency matrix is minus the number of vertices. So all the eigenvalues of the adjacency matrix are negative. So there's explicit formula for this kind of graph given by the four people, PPP. And so it's a complex contour integral formula. And in the integrand has some vertex contribution. And there's the lattice zeta function factor, which looks like follows. There's in fact some Q power. And there's integration variable Z for each vertex. And there's sum over this set. And B is the spin-C structure of Y, which is isomorphic to the one-dimensional homology of Y. And furthermore, there is this principal value prescription PV, which is sum of the two contour integration. One has a circle with radius a little bit larger than 1, and the other circle is a little bit smaller than 1. And after doing this integration, we add them up, their contribution, and take this epsilon go to 0 limit. And here the MIs are the diagonal entries of the linking matrix. Sigma is the signature of Y that appears here. And pi is the number of positive eigenvalues of B. And the next slide is about topological invariance. So two plumbing trees present the homeomorphic three manifold even only if they're related by a sequence of Newman moves. So there are 3 of them. And first one, there can be a plus minus 1 framed vertex with degree 1, and one can either remove it or attach it. And the second move is about plus minus 1 framed vertex at a degree 2, and one can either remove or introduce it at the cost of changing the framing of adjacent vertices. The third move is when there is a 0 framed degree 2 vertex in the middle. One can remove it and collapse the 2 into 1 vertex, or one can split it into 3 vertices. So the formula for the jihad is invariant under these Newman moves. So therefore, this jihad is well-defined invariant for negative definite plummetry manifold. And there has been some. So there are some relations to other spin manifold invariants at as Q go to 0 or at imaginary number I. So Bukov, Park, and Puchra provided evidence for connections to other invariants of rational homology spheres. So first is just the invariant from Hagar flow homology, HF plus minus versions. So as Q go to 0, they showed that this overall factor delta is related to the D invariant in this way up to mod 1. And the second connection is to the Brooklyn invariant. The Brooklyn invariant is defined through a signature of 4 manifold that is bounded by Y. And this four manifold is smooth, compact, and spin. And the key point is this different coefficient, which the author is called Rocklin. So which depends on the spin structure and the spin C structure. So so these three people found what this is. It's some complex coefficient. If you combine with G hat as Q go to fourth degree of unity, and after adding up all the spin C structure, one recovers Rocklin invariant. That depends on spin structure of Y. And another relation is a sixth root of unity. So Kilby, Melvin, and Zhang found the connection between the SL2C WRT invariant and read invariant and read defect. So using their results, I found that the relation to G hat is given as follows. So on the left-hand side, there are a whole bunch of quantities. So first, this read invariant W over Y is actually more precisely called mod 3 read invariant. It takes values in mod 4, which appears here, and there's read defect of the double cover of Y, which also takes values in G mod 4. It also appears in this, appears as a power of I. And this depends on theta, where theta is this one-dimensional cohomology class of first cohomology group of Y in G mod 2 coefficient. And there is this epsilon, which depends on theta, which can be either 0 or 1, depending on what the value of theta is. And there's D of Y, which is the rank of first cohomology group of Y in G mod 3 coefficient. And D of Y of theta, which is the rank of first cohomology group of the covering manifold, also in G mod 3 coefficient. And there's cubic cup product of theta that's in the same ring. So what I found was this complex coefficient. So if you combine that with C hat, and this one takes Q to the sixth root of unity, and add them all of the spin structure, mod G2, one can find this read invariant, especially so this read invariant, this read defect. So the advantage of this approach is that originally this read invariant and read defect, they're all formulated using four manifold that is bounded by Y, similarly as in the Rocklin case in here. Yeah. So this new relation provides a three-dimensional approach to finding this read invariant and read defect. Next, we move on to two variable series f of k. So using the previous G hat integral formula, Gukov and Manolescu introduced a two variable series f of k depends on x and q for plumbed knot complements. So roughly this f of k is G hat of knot complement, where y is integer homologous sphere. So its general form is given by Laurent power series in Q. the coefficient is Laurent polynomial in x to the plus minus 1/2 power. Integer coefficients, and there's also over a factor of q and some over a constant. And computing k amounts to finding this coefficient f of mq. This is actually the series variable part. So, and the Kobe Manolescu showed that the series f of k is invariant under the Newman moves, and so it's invariant of the manifold Y with torus boundary. Yes, I think there's type A. It should be just this. No series here. Sorry about that. And let's move on to the properties of f of k. So a simplified version is f of k has a topological quantum field theory property. So according to the definition of TQFT, one can assign a vector space over field to the boundary of cobordism, which is torus in our case. And f of k is element in this vector space where the field is Novikov field also associated to the torus. And this implies a TQFT for Plum 3 manifold. And next property is dense surgery. So for a knot in integer homology sphere, and performing a P over R surgery produces some 3 manifold Y P over R. And the surgery formula connects G hat with f of k using this Laplace transform curly L, where this Laplace transform acts as transforming this x variable to this q variable in this way. And the next property is connect sum. So under the connect sum, f of k is roughly multiplicative. So this conjecture was verified for connects the sum of torus knots both at the level of f of k and at the level of WRT invariant for integer homology spheres. Next, we move on to another knot invariant ADO invariant. So in early 1990s, the three mathematicians defined the color generalization of the Alexander polynomial for color-oriented knots, or rather links, using R matrices. So the construction of the ideal polynomial for knots link is based on a 1-1 colored tangle diagram obtained by cutting a knot and using quantum group of SL2C at root of unity. As a consequence, the ideal polynomial comes in one parameter family denoted by P, which is positive integer, and this P is tied to the roots of unity. And this polynomial is one variable for knots and multivariate for links. So here is a 1-1 tangle, how one obtains 1-1 tangle diagram. There is a knot and one cuts at the top and the bottom. And one short remark is that when the parameter P is 2, it coincides with the classical Alexander polynomial. Okay. So in 2020, these people found the concrete evidence for a relation between f of k at root of unity and the ideal polynomial through analyzing trefoil, figure 8 knot, and 5-2 knot. And they propose this conjecture that for any knot in 3 sphere, f of k at pth root of unity is related to the ADO in this way. And this is the symmetrized Alexander polynomial with this variable raised to power p. And there's some factor, normalization factor roughly And this SE is the symmetric expansion around x equal to 0 and x equal to infinity of this quantity. And then I analyzed when p equals 4 for this class of torus knot. So when S is at least 7, this ideal 4 polynomials are constructed inductively, can be constructed inductively using a simple algorithm. And ideal 4 of t to 7 and to ideal 4 to t to 13 are initial data for the algorithm. So I'll demonstrate this algorithm by applying to t to 15 knot. So beginning with x to 2s, write a polynomial with coefficient ci following one of the 4 patterns that this class of torus knot belong to. So for our so these are the 4 coefficients, set of coefficients, and for our case, it's the first combination. So just copy down the coefficient and put x equal to 7. So I get this. And the next step in the algorithm is add a polynomial starting with x to the 3s minus 8, following the exponent pattern and coefficients of ideal 4 of t2 comma 2s minus 7. So I'm just getting x equal to 7. So this is the seed polynomial that I mentioned in the previous slide, t to 7. And t to 7 has this kind of a term in it. And so we put x equal to 7. So we have x13. And we just follow the exponent pattern, minus 1, down by 1, down by 1, and here there's down by 2. So I just apply this change of this power here from 8 to 6 for these 2 terms, and then I just copy the coefficients down. And then the remaining polynomials are determined by mirror reflection of coefficients across the last term in the previous step, beginning from the second last term, and adjust the exponent of the variable x following the pattern of the step 2 until constant term is reached. So since the previous expression ends with this term, we reflect the coefficient about this term until a constant term is reached. So here, there's difference in 1 in exponent, so I have x to the cube, and then there's another difference in 1 with x. So I have x squared, and then there's difference in 2 in power, so now I have a constant term. So and then I just copied these coefficients from these 3 terms. The last step is just to use Wiles symmetry to obtain 1 over x term. Just replace all this polynomial with 1 over x. And the first check is that this result agrees with that of the original I matrix method. And f of k, this root of this f of t to 15 force of unity obtained from this results using the conjecture agreed with the formula from the Gukov and Manolesky. And one last remark is that the R matrix approach takes many hours as the family label P and/or the number of crossings of knots increase. However, the FK approach is efficient. So thanks for watching.